Hi, in this video we're going to look at an example of using convolution to solve a differential equation. So we talked about in class the definition of the convolution of two functions. So I'll just go ahead and write that up here at the top. So we use this star asterisk to denote the convolution of f and g. And that is defined to be the integral from 0 to t of f of tau. That's just a dummy variable tau. You could use u or something else, but our book and most books use tau, times g of t minus tau, integrated with respect to tau. And that is commutative, so you could do g star f or f star g, and you should end up with the same thing at the end. So we talked about that already in class, and we looked at one example of solving a differential equation using that, but we're just going to look at another one here. So the first thing I have typed here on the screen is from our table of Laplace transforms, and so the column on the left is the function, and then when you apply the Laplace transform to it, you get what's on the right side, and then the inverse Laplace transform brings you back the other way. And so this is also something we talked about in class. This integral on the left side, you'll notice, is the same thing as that convolution integral. So we could have written on the left column here just f star g. But the idea there is that you can use convolution when you want to take the inverse Laplace transform of a product of two functions. When you do that, you get the convolution of the two functions' inverse Laplace transforms. So we had this in our class notes, but that's essentially what we're going to be using in this example. All right, so let's look at the differential equation here. We've got a second order linear non-homogeneous differential equation. We've got k, an arbitrary constant here. So we could think about the left side of this differential equation perhaps representing a spring mass system with no damping, a spring constant of k, and a mass of 1. Or we could just think about it as just a differential equation. The right-hand side here is just an arbitrary function, f of t, and we will make the assumption here that we can actually take the Laplace transform of that. We looked at some theorems earlier in the chapter about what kinds of functions you can take Laplace transforms of, and so provided that f of t is of exponential order, the Laplace transform of it exists. Alright, so we're going to solve this differential equation using Laplace transforms. So I'm just going to start by finding the Laplace transform of all the terms. So really I'm taking the Laplace transform of the left side equals the Laplace transform of the right side, but on the left side here I'm using that linearity property to separate that into a sum and then the constant multiplied times my second term here. So I kind of skipped a step in there, taking the Laplace transform of each side of the equation, and then on the left side using that linearity property to kind of break that apart. All right, and then I'm just going to go ahead and write down, just like we usually do, the left side at this point shouldn't be too difficult. All right, so all of that I wrote there is the Laplace transform of y double prime. And then I'll have plus k times the Laplace transform of just y will be this capital Y as a function of s. And then on the right hand side here, Laplace transform of a generic function of t. In the same way that the Laplace transform of that generic function of y, we just use capital Y to denote that. On the right hand side here, I can write capital F of s or just capital F. I'm going to write the of s here, but in the next step I'm going to drop that of s off because we're going to be solving for capital Y, and we just end up with kind of too many s's on the right side sometimes. So, all right, so I took the Laplace transform of both sides of the equation. I'm now going to substitute in my initial conditions. So y of 0 equals 0, so that's convenient. That whole term will drop out. Y prime of 0 is 1, so that term will become 1. So I'm going to add 1 to both sides of the equation, and at the same time I'm going to go ahead and factor y out of the terms that are left on the left side of the equation. My goal here is to solve for capital Y and then to use the inverse Laplace transform. Sometimes preparing to do that inverse Laplace transform can be a lot of work just to make sure everything is set up properly to do that. All right, so here I'm going to divide through by s squared plus k. And now it's really about manipulating that right side so that I can get it in a form where I'm able to do the inverse Laplace transform. So the algebra is different problems, but in this one I would probably go ahead and separate that right side into two separate fractions. So I have 1 over s squared plus k, and then f over s squared plus k, or I think I'll actually write that second term as 1 over s squared plus k times f, so that the f is next to it. All right, and so now I want to do whatever manipulation is necessary. Remember, you've got to use legal algebra moves here. You can't just be making things up that don't actually keep the equation the same. But I want to prepare to do that inverse Laplace transform. So for this first term here, we have something in our table that says that the inverse Laplace transform of a over s squared plus a squared is sine of at. So I just need to manipulate the constants a little bit so that I can get square root of k on the numerator here. So I'm going to multiply by square root of k on the numerator, and then 1 over square root of k out front. So I'll be able to do the inverse Laplace transform on that term. For the second term here, I might have to think a little bit harder about that. So I have the 1 over s squared plus k, which matches the same form that I used for my first term there. But the problem is that I have this f here, and that f is not a constant, so I can't just factor that out. But this is where the convolution is necessary. What I have here on the right side of my differential equation in that last term is a product of two functions that are Laplace transforms of some other functions. So I'm going to make the same manipulation with the constants that I did on the first term. I have the product of two functions that are the Laplace transforms of two other functions. So there is my f of s times g of s. And so when I do the inverse Laplace transform of that, that's where I'm going to end up with my convolution. All right, so I'm going to scroll up and go ahead and do my inverse Laplace transforms here. Okay, so I've written out the inverse Laplace transform of both sides of the equation, and then on the right hand side I use that linearity property to separate into two separate terms and then pull those constants outside. And so now I'm ready to do my inverse Laplace transforms. So the inverse Laplace transform of this capital Y is lowercase y. And then I'll have my constant 1 over square root of k. Then this one is the one I've written in pink up at the top. So we will have sine of square root of k times t. And then here I'm going to have my constant out front. And then this is what we were talking about with the convolution. When I take the inverse Laplace transform of a product of functions, I'm going to get the inverse Laplace transform of those two functions, the convolution of those two inverse Laplace transforms. So I'm going to write out an extra step here that I don't usually write out, where I'm going to go ahead and do the inverse Laplace transform on that last term in a couple steps here. All right, so the inverse Laplace transform of square root of k over s squared plus k, that will be our sine of square root of kt. And then I will have that convoluted with the inverse Laplace transform of that function, generic function, capital F of s, and so I will get f of t. So this is convolution, not multiplication at that step. There is my answer written with convolution in that last term. In the homework and in the written assignments that I will ask you to do, I will want you to go ahead and write that as a convolution integral. So that is in our table. I'm going to scroll just back up here and point out that that is in your table here, so you don't have to remember that. You've got that convolution integral there. You just got to recognize that that is what that convolution integral is. And that is commutative, so I can put the t minus tau in the input part of either of my two functions here. I'm going to put it in the sine function in my answer here. All right, so there is my answer written with a convolution integral. And then the idea is that when we started with that differential equation, remember we had just an arbitrary forcing function on the right-hand side. So the idea here is that if you know what that arbitrary forcing function is, or if you want to try out different arbitrary forcing functions, here you've done all the work. You don't have to do all the work to solve the differential equation each time. You could just put those arbitrary forcing functions into here and then evaluate that integral at the end so that you get the solution for lots of different types of forcing functions. So that's the main idea of when you might use this.